In this video, we're just going to review a couple quick concepts and look at how the fundamental theorem of calculus part 1 can be used to ask some questions we've already dealt with in the past. So we want to find the area between the curves, and I've graphed them here. The red curve, of course, is the cube root. The blue curve is y equals x. Now, I want to focus here, first of all, of course, when you're thinking about finding area, you want to find the intersection points. We have 3 intersection points at -1, at 0, and 1. Now, if I were going to integrate to find this area, okay, let's do this one in red. Okay, if I were going to find an integral to find that area, I would integrate from 0 to 1 the cube root of x minus x dx. Okay. Now, for this other piece, okay, right here, I'll do this in blue, I would integrate from -1 to 0 x minus the cube root of x dx. Now, I can do this, pretty easily. I'm going to leave myself some room for work. I just want to talk, first of all, why you couldn't do it in one integral. If you integrated from -1 to 1, tried to do this in one integral, you would get an answer of 0. And the reason is, in the middle of the interval from -1 to 1 at 0, which function is on top changes. We always want to do top function minus bottom. Well, here, from -1 to 0, the top function is the linear function. But from 0 to 1, the top function is the cube root function. So we can't do it in one integral because we have a change in what function represents the top of our area, of our bounded area. So if we do, and these two areas, if you're thinking they look symmetric, they are. They're both the same. That's why we get 0, because not changing bounds, one of these would end up negative. And if they're the same, one's negative, one's positive, of course they're going to add up to be 0. Now, I would probably start by just saying, well, instead of having this be the cube root of x, I'm just going to write right above it, this is x to the 1/3. Let me do that over here too. Always easier to differentiate and integrate exponents than roots. So I raise the power, becomes x to the 4/3. Dividing by 4/3 is the same as multiplying by 3/4. Evaluate at 1 and 0. Okay. If I plug in 1, I'm going to get 3/4 minus 1/2, so 1/4. If I plug in 0, I get 0. So the answer for this area is 1/4. Okay. Over here, on the other side, I get 1/2 x squared minus 3/4 x to the 4/3, evaluated at 0 and -1. If I plug in 0, I get 0, minus, and if I plug in -1, I get -1/4. So, of course, that's 1/4. So the total area, I got 1/4 on the left, 1/4 on the right. The total area is 1/2. This has been a really common AP Calculus AP question the past few years. And it gives us a chance to review some things as well as using the fundamental theorem. Let f be a function whose domain is the closed interval from 0 to 5. The graph of f is shown below. Consider a function g defined by g of x is the integral from 0 to x of f of t dt. So, what this means is that g is an area collector. G is simply collecting area from 0 to whatever x value we want under the function we've been given. So the very first question says, find g of 3. Well, g of 3, let me put my work down here. G of 3, that would be the integral from 0 to 3 of f of t dt. So we're just finding the area from 0 to 3. Well, we've got some positive area, right, up here, this little trapezoid, which, you know, you could break into parts or you could add up or something. I'm going to actually use a trapezoid. It's going to be half base 1, which is 1, base 2, which is 2.5, or 5 halves, and the height, which is 1. Okay, remember the bases are the parallel sides. So 1/2 multiplied by 7 halves is 7/4. Okay. This other little portion here is a little triangle. Okay, it's going to be half the base, which is 1/2, and the height, which is 1. Well, that's just 1/4. But of course, that's negative. It's below the axis. So to solve this, I say, well, I have 7/4 and negative 1/4, which of course is 6/4, or 3 halves. So 3 halves is G of 3. Okay, I'm just going to clear this out just so I got room to draw. Okay. Next, on what intervals is G increasing and concave down? Well, this kind of goes to fundamental theorem part 1. What I've been given is that g of x is equal to the integral from 0 to x of f of t dt. But if I take the derivative of g and get g prime, and whatever you do to one side, you have to do to the other. So now I say, well, I'm going to take the derivative of g, I get g prime. If I take the derivative of this, the derivative of the integral is just the function. It's just f of x. So here I've been told I've got the derivative of, or the graph of f, but really I have the derivative of g. So, you know, when is g increasing? Well, use derivatives. This is when g prime is greater than 0. When is g concave down? You could either say it's when g double prime is negative or when g prime is decreasing. So where does that occur? Where is the derivative? Remember, the derivative is the graph we've got. Where is the derivative positive but decreasing? Well, that occurs from 2 to 2.5. And show your reasoning. Well, this is where the derivative, the graph we have, is greater than 0 and decreasing. Okay. So we really just were able to use fundamental theorem part 1, you know, the derivative of the integral, to show that we actually have a derivative graph. You know, g prime is this graph. And it makes a pretty easy question. We did these before, but of course it looks very complicated, and it adds one kind of wrinkle to this where you had to do a little more work than just say, oh, I've got the derivative graph and I'm ready to go. But it is what you have, okay? Finally, part C, find the equation of the tangent line. Well, for every tangent line we need a point, we need a slope. Well, the point, of course, it told me x is 3, and, you know, to find the y value, we just say, well, I put 3 into g. Well, I already did that. I did that in part A. So the point is 3 and 3 halves. Okay. The slope, well, to do slope, I need the derivative. So I need to know what g prime of 3 is. So you go up here and you say, well, g prime of 3 is negative 1. So my tangent line is y equals, let me just write down that this was negative 1. My tangent line is negative 1, the slope, multiplied by x minus the x coordinate plus the y coordinate. There's my tangent line. So a bunch of questions that weren't terrible to answer. You just needed to kind of be careful and use fundamental theorem.